Homework 8, Inverse Functions, Video 1. In the previous series of videos, we looked at different ways to combine two functions, to add them, to subtract them, to multiply them, to divide them, and to find their composition. In this next series of videos, we're going to talk about inverse functions, namely functions that undo the actions of one other function. For example, if I had a function, let's say I'm a function, you give me a number, and I'm going to double your number. So you give me a 3, I will give you back a 6. If you give me a 10, I will give you back a 20. If you give me a -1/2, I give you back a -1, etc., etc. What function could undo my action? For example, somebody gave me a 3 and I turned it into a 6. What could somebody do to that 6 to turn it back into a 3? They could cut it in half. Isn't that the opposite of me doubling things? Or it could be even more convoluted. For example, let's say that my function will double something and then add 1 to it. So somebody gives me a 5, I double it to make it a 10, I add 1 to it to turn it into an 11. So they give me a 5 and I turn it to an 11. What would an inverse function do to that 11 to turn it back into the 5? Well, first they would have to take the 1 back off, and then they would have to divide by 2. So again, somebody gave me a number, I doubled it and then added 1. Then this person takes off the 1, divides it back in half, and gives me back what I started with. So that's the idea of inverse functions. One function will do something to another, to a number, and turn it into a new number. The inverse function will take the new number, undo what was done, and give you back the number that you started with. Keep that in mind as we go over this definition. A function f of x is invertible, meaning it has an inverse. If there exists another function, we'll call it g of x, such that 4 things have to happen. Number 1, when I do f of g of x, I get back x. In other words, the result of doing this composition is just an x for every x in the domain of g. Why does it have to be in the domain of g? Because remember that f of g of x literally means f of g of x. So whatever that x is has to be able to go into the g, hence be in g's domain. Number 2 is the same thing except in reverse. G of f of x equals x for all x in the domain of f of x. In other words, this x has to be able to go into the f, therefore must be in the f's domain. And g of f of x literally means g of f of x. So it's the whole let me undo what you did idea. This function f will take this input and turn it into something. This g will take that something and unravel it and turn it back into what you started with. The other 2 criteria are a little bit trickier to explain, but they're not that bad. The domain of f has to equal the range of g and vice versa. And the reason is really simple. Go back to the first one. If I put a number into this composition, it has to first go into the g, but at the end it has to come out of the f. So whatever goes into the g must be able to come out of the f. Whatever's in the domain of g must be in the range of f. And vice versa here. Whatever I put in here must first go into the f and eventually come out of the g. So if it goes into the f, it's in the f's domain, and if it comes out of the g, it's in the g's range. Really what we're going to be focusing on mostly is that this composition in both directions ends up just giving you the x. We may, we may get to an example of where this is a little bit more important. Oh, before I pause this video, if a function has an inverse, that inverse is also called, it looks like f to the -1 power of x, but it's read f inverse of x to explicitly say that I am the inverse of this function. Well, so let's take a look at some examples and then we'll talk more about the domain range thing and are there functions that are not invertible?